So Prikry sequences, right? The classical case, I'm going to start with a classical reformulation of Prikry forcing. Usually, if you have a kappa measurable, and you have U a measure on kappa, and you look at the iteration of V via U and its images, then you have that the critical point sequence is Prikry generic over the final model, and it's cardinal preserving, and yeah, it's a very useful forcing. People use it all the time. And then there is a super general version of this theorem due to Itai Niemann, which is in his paper, Inner Models in the Region of Wooden Limit of Woodens. And where he essentially, I will not write down the full statement, I will just draw a picture. Essentially, what he proves is that suppose you have V, and you have a countable iteration tree U on V, such that it picks cofinal well-founded branches. Unique, that's the important part, unique cofinal well-founded, of course. Yeah, and you take a hull of this picture. So you'll have your V bar, and then you will have, well, it was countable, so you will get a tree U bar with the same tree structure, and suppose this guy has a final model M alpha U, and call this map pi, and call this guy. This guy will be M alpha U bar, the final model of this guy. And essentially, if you restrict pi to V bar and do the copying construction, this final map will be pi restricted to M alpha U bar. And the claim is that this final copy map, pi alpha, is generic over M alpha U by a forcing that has rho less than alpha U plus CC, essentially soup of the generators of the extenders used here plus CC. And, well, you can ask, how is this a generalization of this? You essentially just need to note that by taking a countable hull, you can translate between these copy maps and sequences of generators of the measures or extenders used. All right? So what do we want to, so what's the theorem that we want to prove? For the setup, let's take an extender E such that length of E equals the strength of E is inaccessible. Let lambda less than omega 1. So what we want to show is that given a nice enough extender, if we iterate it countably many times, and if we take any countable sequence of generators and we look at the thread given by that, that will be generic over the final model. All right, so to just write it out, we have our extender. This is the length of the iteration, and A is a countable set of generators of E. Yeah, and you look at the iteration M alpha, pi alpha beta, alpha less than beta, and the iteration of E and its images. So the theorem is, this is the thing that's in my master's thesis, so with Ralph. The sequence I0 alpha I0 alpha of A, alpha less than lambda is generic over n lambda by a cardinal preserving forcing that has the Prikry property. All right, the main point of this essentially is a refinement of Neumann's theorem, but now the forcing is cardinal preserving, and also, well, this is the same, essentially the same hypothesis that you would need for Neumann's result, but you can reduce this to as low as a measure of Mitchell order omega 1. Yes? So this is the thing, so this in the case of, yes. So in the case of Prikry forcing, it's just the critical point sequence, right? But here you want to take any countable set of generators, look at the thread, and that guy is generic, right? So this is the main theorem. First, before I say anything, I will just set up a small piece of notation. So if F is an extender and X is any set in the ultra power of V by F, we can define the component measure at X, right? So what we can do, we can essentially look at let lambda be least such that X is in pi FV of V lambda. Then you can say, so for any Y subset of V lambda, you can just set, Y is in Fx, if and only if. Is in the, it's just a usual component measure. You can show that this guy is a normal measure. All right, so the whole point of this thing is that there's some combinatorial setup to do it for general lambdas below omega 1, but since it's a bit messy to do it in a talk, I will just go to the base case where, so assume lambda is just omega times omega. And also further, just to avoid lots of unnecessary notation, let's also assume that A is just crit E. And also let's set up more notation for I less than or equal to lambda, omega times omega, kappa I equals crit of I0 I of E. Okay, simple enough. All right, so I will first sketch the idea in a picture, then we will go into defining the forcing, and I will try to convince you that the usual argument for Prikry forcing, where you use this game to show genericity of the thread, it works. Right? That's the idea. That's the picture. So what's the idea? All right. Which line? Assume that lambda is omega times omega, just for avoiding lots of messy combinatorics. All right. Yes. Yeah. Also, let's not deal with any countable set of generators. Again, it's just extra notation, but it works. And once I write down the forcing, it will be easy to see how you would modify it. Well, not for this guy, not for increasing this guy, but for this guy. It will be obvious. All right. Okay, so in terms of a picture, what we're doing is this. So I will draw a picture for the iteration, right? So for example, let this be M0, you have M1, and here you have M omega, the first limit stage of the iteration, and then you reach, you reach M omega times 2, you go ahead. Bigger, all right. All right, okay. Okay. This is M0. So you reach M omega, and then dot, 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 you reach M omega times 2. And this is, let's say, M omega times N. I will just write these. This is M omega times omega. All right? So usually in terms of, in Prikry forcing, what we do is you take a measure here, and you start looking at, like, okay, I'm interested in doing tree-style Prikry forcing. So essentially you have a tree that splits in measure 1 sets above its stem, and those measure 1s come from measure here. Of course, we cannot do it here, because, for example, if you just use one measure here, there's a dense set that says almost a tail end of the generic is above, for example, a kappa omega times n, right? So that obviously doesn't work. So next idea, so in order to refine that, what you need to do essentially is start choosing measures at each step, at each limit step. So at each step, I will choose some measure like this. All right, and then below that limit step, I have these successor stages, and I will make sure that the ordinals that I'm choosing that are going to be the Prikry sequence at M omega, so at below kappa omega, these will be guided by measure 1 sets from this measure, right? And then you might ask me, well, this surely shouldn't work, right? Because how are these measures related? There's no correlation. It seems like there's random stuff going on. And it's pretty hard to control it. So what you do is you force it to be compatible. So here, instead of choosing just one measure at M omega times omega, you choose 2 measures. All right, we are also choosing points. Right, remember, we need to find the kappa omega as well. But you choose 2 measures. This measure is measuring measures that measure points, right? So in order to choose these measures, so this measure guides our choices for these measures, right? And these measures guide the smaller choices. So that's the general picture, right? So yes. Yes. It is an omega squared sequence, right? I'm also, sorry, I didn't write it. So I'm also choosing points here. So these are the Prikry sequences that are becoming cofinal in kappa omega. And there are points here. Yeah, sorry. Yeah, kappa I, let me write it bigger. It's okay. Yeah, sorry, I'm kind of not used to this big of a class. So, all right, so, but how does this picture emerge? Well, you can see it's unfair to compare this guy to these guys, right? Essentially, there's a combinatorial structure here where essentially you have a tree at the bottom, you have omega times omega. And here you have omega times 2, omega times n, blah, blah, blah. And then here you have 0, 1. Here you have omega plus 1, blah, blah, blah. Right? So the points that are converging to omega times omega are these guys, and then each of them has their own Prikry sequence, right? So essentially in the general case where I said I'm avoiding the combinatorics, you do this sort of a tree construction. So you give complexities to each node, and that gives you how deep you need to go into this game of having measures of measures of measures of measures of measures, right? That's where this thing comes in. All right, so how do we manage with the coding? Now, in general, when I have a condition, what I want, so conditions look like this. it's a tree, it has a stem, we split above the stem, right? So I want in the bottom, because I said I need to be guided, right? So in the bottom node, I determine this guy, right? In the next node, I make sure to determine this guy, right? At the next node, I'm free. I can either determine this guy, or I can go start determining from the first sequence that's converging to this guy, right? Trying to extend the stem, finding concrete points, right? So in order to do this, we just take a coding function E from omega to lambda plus 1. Oh, no, sorry, omega times omega plus 1, where we just demand that 0 gets mapped to this guy. So the first stage, we choose this extender, and then all of these guys appear later. So I will write it down. E inverse of omega times n is strictly less than E inverse of omega times n plus 1. And also, we don't want these guys to appear before this guy appears, right? Because it needs to be guided. So naturally, you always assume that E inverse of omega times n is always strictly less than E inverse of, is this big enough? All right. Oh yeah, I will bring it up, all right. E inverse of omega times n plus k, right? Okay, not too high. All right, now we are in good shape to define the forcing. Right? It's exactly what you expect. Now that you have the picture, you essentially, so it depends on this coding function E, of course, and then you say, my tree is inside, if and only if, well, T is a set of, it's a tree of finite sequences S with stem T, ST, S sub T, such that, so there are two main things we want. First, we want to describe what we do at each point. So for every n less than the length of S, I want to define what S of n must be. So, if n is equal to 0, this means I need to identify this guy. So here, I just demand that I have a sequence of length 3, but I identify it as a tuple. Some alpha f prime, such that alpha is so f and f prime are extenders, alpha is the critical point of f, and I make sure that alpha f is a component of f prime, because later on, that will give me the measure I need to find these guys, right? So you demand that alpha f is in the ultra power of v by f prime. And now suppose E of n is one of the other limit stages, is like omega times k. Well, in this case, I just take an alpha f, where alpha is the crit of f. And lastly, otherwise, it's just a sequence of length 1, and it's an ordinal. Nothing special. All right? And yeah. All right. Yeah, small thing. Whenever I write the rank of a point, so rank of this guy is, what is it? It's 2. Rank of these guys is 1. Rank of these guys is 0. Right? Okay. So now we need to talk about the splitting, right? So, and B, we say if S is extending the stem, we demand that, all right, so let n be the length of S. So this is the next point that is supposed to be added. And so you must look which point of the iteration it is. right? So it's some omega times k plus L. And then it makes a difference. If, so, let's m equals 0 or, yeah. If L is equal to 0, let m be 0. Otherwise, it's positive. Let's be E inverse of. I will write out and then I will expand. All right. All right, so I want to find the right measure one set for the extensions of S at the point N, right? So it depends. So if this N is a point like this, I need to find a point and an extender on top. If it's a successor point, I just need to find the point. And this is the M that I'm choosing here. The M is just telling me what do I need to code, right? If L is 0, it means I'm at omega times k. So I'm at one of these omega times k stages. So I need to. Is this clear, or should I explain more? More. Yeah. I see. All right. Maybe it's best if I split it into two cases, so that would be easier to see. So in the case that L is 0, we know that En is omega times k. So we want that the set of all S, this is in T, sorry. T. All right. So En is omega times k, and I need to consult the measure at omega times omega, right? So where is that guy? I need to look at S of 0. Remember, it's only at 0 that I have this measure that's guiding me. All right, so I need to look at its second component, at this like second extender, and then I'm looking at the alpha F's, right? Restricted to 2, right? When I restrict the sequence to the first 2 points, I'm looking at the alpha F's, I'm looking at the measures, right? So this is the component measure of this extender, right? Nothing fancy going on. I'm just consulting where I am and then looking at the corresponding measure and choosing my points. That's it, right? Okay. So. You have until 5, right? You have until 5, right? Or before? How much time do I have? Yeah, perfect. Yeah. All right. Okay. So that's the definition of the forcing. Right now, I will try to convince you guys that if you run the usual argument that Prikry forcing as a Prikry generic, then they're done. Okay. All right. So I need to now tell you what the Prikry sequence is. That just needs one small definition. That just needs. I will choose points gamma 0 and gamma 1, closure points below the inaccessible length E, so that the extender E restricted to gamma 0, the strength of it is gamma 0. And same for gamma 1. Because length of E is inaccessible, we can do that. So yeah, the reason I'm not talking is because of this. Yeah, I think I'm far enough. So if, now, we want to define the sequence. As I said, at the end, we want to have these two extenders. One of them is stronger, and it's measuring the extenders that are supposed to measure the other points. So this will, the role will be played by this guy, and this will be the smaller measure. If we are in an intermediate level, we just look at the okay? This is just what I described over there. And then so we have that every initial segment of Z is in is it? Oh, is that okay? All right. Yeah. Every initial segment of Z is in M omega times omega because the extenders were strong enough, and we just left behind all these initial segments, right? That's easy to see. So this is going to be our generic. So all the trees such that Z is a branch through the tree. And well, it's easy to see that G is a filter, right? Because all the measures have enough completeness. You can just have meets in this forcing. I think it's kind of easy to see. We just need to show that G intersects every dense set. So let the subset of PE be dense and D in M omega times omega, right? I hope it's easy to read. So we have this dense set, and we want to show that G intersects it, right? So what's the idea? Usually what we do is this dense set is generated via some generators that come from some points in the iteration, right? You hit all these extenders, and the generators of these extenders will generate the full model. So we can suppose that, so let n0 less than omega be large enough so that D is supported by E pointwise image n0. So E is determining the different points in our iteration, and if all of the generators already appear at this point, we say it's just D is supported by D pointwise image N0. Now here comes this game, which I don't know if it's due to eta Niemann or not, but I don't know. Maybe somebody knows. So define the game GD. So we have two players, player 1, player 2. They are playing, so player 1 is playing some large set, player 2 is picking points in that large set in the following manner. So we've already played up to n-1, let's say. So letting all right, so we assume that, so what are we trying to show? We are trying to show that in the dense set D, there's a tree with stem Z up to N, all right? So we start with bottom part Z up to N0, and we start playing this game. Player 1 plays large sets so that it's compatible with the structure of our trees, and then player 2 starts picking points in those large sets, trying to extend the stem, all right? So if you want to write it down, player 1 picks. So yeah, again, there's the coding, letting E of n be omega times k plus L. From now on, I will assume we are in the successor steps because it's easier to deal with the coding, all right? I will assume that L is greater than 0. So what does player 1 pick? Player 1 consults the, all right. So let M be such that E of M is omega times k plus 1. So remember, if L is positive and we are at omega times k plus L, we are one of the points that's trying to converge to kappa omega times k plus 1. All right? So we need to choose a measure from what what S says about this point of the iteration. Right? So xn must be an element of the component measure of S of M at 1 restricted to S of M, cut off at 1. So remember, this was a critical point of this extender. This is just a derived measure of this extender at its critical point. Right? Remember, this was a sequence of, so this guy, S of M, to write it like this, is some alpha F, where alpha is a critical point of F, and this is just a derived measure at alpha, the critical point. All right? Okay, so we pick this, and player 2 picks xn in xn. Now, all right, 2 wins if and only if there exists a finite stage n, there exists a tree T in the dense set that we started with, and it's in a way so that Z restricted to n0, followed by small xn0, blah, blah, blah. Xn is the stem of this tree. Okay? Pretty simple. So as you can see, this is a closed game for player 2. Right? So it has a winning strategy, and I hope it can be easily seen that player 1 cannot have a winning strategy. Right? So I will write it as a claim, and I will just do a proof by hand waving. Okay. Claim. Player 2 has a winning strategy. All right. What's the proof? So the game was close. Somebody must have a winning strategy if it is player one. So what does player one do? Player one is picking measure one sets, and player two can respond with any point in that measure one set. So what do? You take player one's strategy, and he plays some measure one set, and you keep responding with every possible value in that measure one set. And inductively, you keep doing this for every response they have. And then this gives you a condition in the forcing, right? And this condition cannot be extended to a condition in the dense set D, which is a contradiction. And the reason is, if you extend it to a condition in D, we'll just keep playing in the stem of that condition. You will defeat it. So I think it's a pretty standard argument, and I think pretty simple to see, right? Unless somebody has a question. All right. So this is good. All right. Now, let sigma be a strategy for 2. Okay, I promise we are at the end, so yeah. We build a sequence xn and 0 less than omega, such that, all right. So the partial play of the xn's is according to sigma. It just means that if you play xn 0, and here you play zn 0, and keep playing xn and then zn. So as player 2, you respond with the z, but you demand that this is a play by sigma. And also at the same time, you don't want to increase the complexity of xn too much. So xn is supported by e pointwise image n plus 1. Right? I will tell you where the second part comes in. It will help us put this point in, essentially, the next point. Right? So, all right. So suppose I have built this guy up to n minus 1. So suppose n minus 1, good. And we want to build it at n. So what do we do? The idea is that essentially you look at the set of all points that there is a response. You have xn0, you have z of n0, you have xn minus 1, z of n minus 1, and here you have y. So x was a sigma response to a possible set y. Okay? So this is a play by sigma. Okay? So I claim that this set is measure 1 in the correct space. Right? And what does that mean? Claim. Let's quickly verify it. All right. Before I do it, I need to again set up the thing. So remember, we are trying to find xn. So let E of n again be omega times k plus L. Again, we are assuming that L is positive to avoid combinatorics. So let M be E inverse of omega times k plus 1. So this is the measure we need to consult in order to find the point, the Prikry point, the point of the Prikry sequence at this level, right? So the claim is x is in Zm1 right? Again, same notation. This guy is a measure. This is its critical point. This is the derived measure at the critical point, right? Because we are at these omega times k case, right? All right. So we want to show this is measure 1. But all right, let me rewrite this properly. So what is this guy from the definition? This is pi 0 EM of E restricted to gamma 0 at pi 0 EM of kappa. This is exactly what it is, right? Can I erase this, or should I erase it? All right, sorry. I will rewrite it in a better way. So. Right? Is this more readable? So you go to the stage EM. So this was the guiding measure at that point, right? And then you look at its derived measure at kappa, at its critical point. And we claim that this guy is measure 1, right? Because remember, these possible x's are from this level, right? Just by the definition of the game, if you follow the combinatorics. All right? So why is this guy measure 1? Well, because otherwise you would have that, the proof, otherwise y equals, so what is this? This is kappa EM minus x would be measure 1. But then y is a possible thing I can play here, right? Now look at the sigma of this play, which I will just denote as sigma of y, okay, just for brevity. But then the sigma of y, well, this y. Now, but because of the constraints on the game, remember that player 2 must choose elements from the measure 1 sets. This is in y. But also from the definition of x, it must also be an x. I mean, this is an obvious contradiction, right? So, all right. So x is measure 1. And just by looking at the definition, you can see I didn't use any crazy amount of generators. We only used up to E pointwise image n, right? This guy we know is supported by E pointwise image n minus 1, no, n. And this is generators below stages n, right? So this is supported by, so now x is supported by E pointwise image n, and it's measure 1. Measure 1. So just by an easy calculation, which I will not write down, we don't have enough time, z of n is an x, right? Now let xn witness z of n is an x. This completes now we have found our xn. But now you can see, if you start playing the sequences xn in this game, at some point sigma must win. But look, we are playing the z's. So you will find the condition in D with stem initial segment of z. So this shows that z is PE. Sorry, G is PE generic over m omega times omega. And just a final note about the cardinal preservation is that if you look at the forcing carefully enough, you can see that you can actually always, so with respect to the iteration, at every limit stage, you can factor it into 2 parts. And the bottom part will be kappa omega times n plus cc, and the top part will have the Prikry property. So between those 2 critical points, kappa omega times n, and kappa omega times n plus 1, you will not collapse any cardinals, right? Because the bottom part has the CC, the top part has a Prikry property, doesn't add any bounded subsets. So all cardinals between the kappa alphas will be preserved, but the kappa alphas are limit cardinals. So everything will be preserved. That's it. Unfortunately, I'm not really well versed in the area of forcing. So I've actually never seen Raiden forcing. So I'm sorry.
If you're around next week.
Yeah. Nice. Yeah. All right.
So I don't get a lot of this. Two has a strategy, right? So how can you force them to pay these? Oh, I see you showed that it is a possible plan. Why does it have to be?
You mean?
Because, yeah, sure, but why does that not apply? Just given the strategy, right?
Yeah. So the main.
There's many numbers you can play because there's no numbers in the set. So why does this strategy?
Yeah, exactly. So the main point is that the dense set is supported by E pointwise image n0, right? Essentially, past the iteration at n0, you're not using more generators, right? And also sigma. So essentially, this dense set goes back to that level of the iteration. It goes back to M E n0, right? And the sigma is of the same complexity, right? Because you know definably that there's an iteration strategy. Suppose you have a fixed bell ordering, choose at least one, right? It goes back to the same level. And then, so at the first part, so suppose we are trying to find xn0, right? So if we find this x, where is it? Oh, yeah. We find this x, and we know it's supported by E pointwise image n0, right? Because there's nothing here, right? And it essentially mentions the game, just the game. And point is, we showed that it's measure 1, but look, what does it mean to be measure 1? If you take the j of it, like from kappa, from E, okay, I need to be correct with the indices. Let's say it's at some index alpha. When you look at kappa is in j alpha plus 1 of x, right? And that will remain the same way all the way, right? So essentially, you look at the preimage of x at the level alpha, but then we'll call it x bar. But then kappa will be in pi alpha plus 1 of x bar, and then from that point onwards, the critical points are so high enough that it won't change kappa being in that set.
Yeah, sure.
Yeah.
I totally get that. This is an element of
Yes.
But you're clearly here, this is the only possible.
No.
There is one
Yeah. I actually don't get what you're saying. The point is, I'm just looking at all the x's such that there is something that you can play here.
You said sigma is the winning strategy.
Yeah.
Why is sigma?
Yeah, so the point is, sigma is using like bounded generators, and above that point, these z of n's are like indiscernibles, right? They get into everything, essentially. So that's the main point. Like, I know, because these x's are measure 1, so z of n naturally gets in. I don't know. The proof. Uh-huh. Yeah. So the main point is, suppose we can go both directions, right? So let's apply ESI theorem to a linear iteration. So what does it say? You have a linear iteration of V, you take which is of countable length, you take a hull of that, and then the last copy map is generic, right? And so which direction should, let's see, let's do the easier direction first. Yeah. So we want to show that the copy map is generic, right? But point is, just look at the pointwise image of the extender used, right, in this linear iteration from the countable side. Yeah. I'm not claiming that this theorem just in general gives that, right? I'm just claiming in the special case of a linear iteration, these are essentially equivalent. And then you look at pi pointwise image of that countable thing. It's a countable set of generators, and then you make that thread generic, but that's already the copy maps, right? Essentially by taking hulls. No, it's cardinal preserving, and also you need much less large cardinals to do it. So in his case, he uses extenders. So in this case, I also used an extender that has length equals strength. It's inaccessible, but you can but with much more coding, you can get away with something as low as a measure of Mitchell order omega 1. So you don't need to go that high to achieve this, at least for linear iteration.